Rectangular hyperbola. So what is a rectangular hyperbola? It is a special case of a hyperbola where the length of transverse axis is equal to length of the conjugate axis. That is, if I take the parabola, this hyperbola, this in the standard form as x and y axis, then length of transverse axis, which is between A and A dash, that is between those two sides, which is 2A, and must be equal to length of the conjugate axis, which is also to be, in this case, called rectangular hyperbola. We have 2A equals 2B. That is, length of transverse axis is equal to length of conjugate axis. Length of transverse axis is equal to length of conjugate axis. That implies A is equal to B. So for rectangular hyperbola, the condition is equal to B, or length of transverse axis is equal to length of conjugate axis. Rectangular hyperbola is a special case of a hyperbola where A is equal to B. Now let's derive the equation of rectangular hyperbola. Now we know that rectangular hyperbola is a special case of an hyperbola where A is equal to B. So here we're going to take the equation of rectangular hyperbola as a special case of an equation. So as we have here, the standard form of equation of hyperbola, as we know, is in this form. So for rectangular hyperbola, I have the condition A is equal to B. That implies x squared by A squared minus y squared by A squared equal to 1, where B is replaced with A out here. So in this case of B gets reduced to A. Then that implies I get x squared minus y squared equal to A squared. Is how I identify the equation of rectangular hyperbola is x squared minus y squared equal to A squared, where 2A is length of transverse axis or the conjugate axis, where I can say that A is half the length of transverse or conjugate axis, is how I derive for A. So therefore, for rectangular hyperbola, only have A but not B, simply because A is equal to B. Substituted reduces to x squared minus y squared equal to A squared. Now let's find the eccentricity with hyperbola. The condition is A equal to B. So with this condition of A equal to B, my eccentricity is related with this, such that E squared is A squared plus B squared by A squared. So we had the eccentricity derived with this as the formula. Now A equal to B implies E squared reduces to A squared plus A squared by A squared using A equal to B. Now again, this on further simplification gives E squared equals 2A squared by A squared. And this gets cancelled because A is not equal to 0. Both A and B are not equal to 0. I have this which can be cancelled. Therefore, I get E squared equal to 2. Now this leads to E equal to plus or minus root 2, which I take on the right. But I don't take the negative side because since E is greater than 1, Therefore, I have only one value for E, that is root 2. Therefore, I conclude that for rectangular hyperbola, the eccentricity is root of 2. So, the condition for rectangular hyperbola is E equals root 2. This is the condition for rectangular hyperbola. When eccentricity is root 2, or when SP by PM is root 2, then this leads to the locus, which is a rectangular hyperbola. The locus of points derive a rectangular hyperbola if the eccentricity is root 2. That is, SP by PM is equal to root 2 in the ratio. Now next is auxiliary circle. Now what is auxiliary circle for an hyperbola? As we see that an hyperbola has both transverse and conjugate axis, we have this x-axis, y-axis, and this is origin. Now using this, we are going to describe the auxiliary circle taking the length of transverse axis as the diameter. So if I take the diameter A and A dash and describe a circle along that, then we call this circle as auxiliary circle. So this is called auxiliary circle, and its center is origin and its radius is simply A. As can be seen, the distance from center to A is small a. So radius is A and the center is origin, is how we identify the auxiliary circle. Now we know that if the center is origin, for an auxiliary circle, the center is origin and radius is A. Therefore, equation of auxiliary circle would be in the form. Therefore, equation of auxiliary circle is given by the equation x squared plus y squared equal to a square. An auxiliary circle is described for a transverse axis as the diameter, and its center is origin and radius is a, and equation of this auxiliary circle is x squared plus y squared equal to a square. Now let's discuss about the parametric equations of hyperbola. Now as we have discussed the parametric equations of a circle, a parabola, an ellipse, etc., similarly we have the respective parametric equations for an hyperbola. To discuss in the session about parametric equations of hyperbola. So here I take the standard form of hyperbola, which is with x-axis, y-axis, and then I get out here like this. Now for this, I have the equation of this hyperbola is given by x squared by a squared minus y squared by b squared equal to 1 with a greater than b. Now for this, if I take any point P out here, then let me join the center of hyperbola with the intersection this point P. And let me say this point P makes an angle theta in anti-clockwise direction. Then this point P is said to have the x and y coordinates connected with angle theta and with A and B, because if I have x equals A secant theta and y equals B tan theta, then these two parametric equations clearly satisfy the hyperbolic equation, as when substituted with x as A secant theta whole square by A square minus B tan theta whole square by B square, which is the left hand side of substitution, gives us this on A square by A square cancelled, secant square theta minus tan square theta, which is equal to 1. That is right hand side. That is, these two equations satisfy the hyperbola x square by A square minus y square by v square equal to 1. Therefore, every coordinate P is given by A secant theta and B tan theta, and this is called the parametric point. And the parametric equations of the hyperbola 1 are given by x equals A secant theta, y equals B, this with 0 less than or equal theta less than or equal to 2 pi, because theta ranges from 0 to 2 pi in one full revolution or rotation of the angle. So theta ranges from this, and the parametric equations of the parabola in standard form are x equals A secant theta and y equals B tan theta. Now let's discuss about the parametric point of the hyperbola. Now, as we know that the point on the hyperbola can be taken as coordinates with A secant theta and B tan theta, where theta is the angle made by the center of hyperbola with the point along x-axis in the anti-clockwise direction. So this theta connected with the coordinates of P or any point on the hyperbola are very much connected with the parametric point. A point which is taken generally in the form P of theta, which is A secant theta and B tan theta, is called the parametric point for the given hyperbola. So any point on the hyperbola can be expressed as A secant theta, B tan theta for that respective angle theta lying between 0 and 2 pi, and that point denoted by P of theta is called the parametric point, and theta is called the parameter because this measures the point. As the angle changes, the point changes. So this is the criteria for changing of the point, and hence it is the parameter or the decision factor for the parametric point. Theta is the parameter, P of theta is the parametric point of the hyperbola x squared by A squared minus y squared by B squared equal to 1 with A greater than B. Conjugate hyperbola. So what is a conjugate hyperbola? An hyperbola with transverse and conjugate axis interchanged with the original hyperbola is how we define the conjugate hyperbola. So let's see how we define the conjugate hyperbola in today's session. Let me take the equation of hyperbola in standard form with x-axis and y-axis out here. Suppose I have the hyperbola S is x squared by A squared minus y squared by B squared minus 1 equal to 0 with A greater than B, then I would like to define the conjugate hyperbola for this. In that case, my transverse axis, which is 2A, will act as the conjugate axis for the hyperbola. We are interchanging the conjugate and transverse axis, so this length gets here and this is a dash, and b dash. So if I draw a hyperbola passing through this and passing through this hyperbola is called the conjugate hyperbola of this. So this hyperbola is called the conjugate hyperbola because its transverse axis is the conjugate axis of the hyperbola, and its conjugate axis is the transverse axis of the original hyperbola. So with those transverse and conjugate axis interchanged for this hyperbola is called the conjugate of the given hyperbola this. So if transverse axis is interchanged with conjugate axis of either of the hyperbolas, we get a conjugate hyperbola. Now, as we know that the equation of the original hyperbola is x squared by a squared minus y squared by b squared minus 1 equal to 0 with a greater than b, then equation of conjugate hyperbola is given by s dash equals x squared by a squared minus y squared by b squared plus 1 equal to 0. Is how I identify the equation of conjugate hyperbola, which is x squared by a squared minus y squared by b squared plus 1 equal to 0 with a greater than b. So these two hyperbolas differ by minus 1, which is for original, and plus 1 for the conjugate. So they differ by the sign of unit 1. Minus 1 to plus 1 and plus 1 to minus 1. Conjugate hyperbola of the given hyperbola. Now let's see some properties connected with conjugate hyperbola, that is, what is the focus or the foci, directrices, and various other properties of conjugate hyperbola. So as we take the parabola in standard form connected with conjugate, is how we get for the conjugate hyperbola has the foci S and S dash and B dash, and of course A and A dash, is how we see each of the properties of conjugate hyperbola. Now the foci of conjugate hyperbola are 0b, with equation of conjugate hyperbola is x squared by a squared minus y squared by b squared equals minus 1. So here S is this, and S dash is 0 minus BE, and coordinates of B is 0b and 0 minus b. My A, which is a comma 0, and my A dash, which is minus a0, and C, which is the center of hyperbola or conjugate hyperbola, is given by this, and length of transverse axis, that is, if I take the transverse axis of this, it is BB dash, because as I see the hyperbola is constructed along this, so BB dash is the length of transverse axis, and BB dash is nothing but 2B, and length of conjugate axis, which is AA dash, is given by 2A, which is nothing but 2A units. So length of transverse axis and length of conjugate axis are given by 2B and 2A respectively. Is how we define each of the properties of foci, the center, coordinates, and all other properties which come in conjugate hyperbola. Even the directrices can be defined by taking a line and then defining the equation with respective properties. Conjugate hyperbola is connected with hyperbola with the equation this and the following properties. The directrices which pass through this are given by the equations y equals b by e and y equals minus b by e, because each of the directrices are b by e units from the x-axis, that is x and y. So the directrix on the top is given by y equals b by e, and the directrix below is given by y equals minus b by e, and the eccentricity which we have for conjugate hyperbola is a squared plus b squared by b squared. That implies E equals root of a squared plus b squared by b squared. Is how we define the eccentricity for conjugate hyperbola. Eccentricity is root of a squared plus b squared by b squared out here. Rectangular hyperbola of the conjugate hyperbola. Now that we have discussed about the rectangular hyperbola, now we're going to discuss on how the rectangular hyperbola looks for the conjugate hyperbola. So as we have discussed about the conjugate hyperbola, to be with interchanging of transverse and conjugate axis, its rectangular hyperbola would be with a equal to b. So I get this equals this. A conjugate hyperbola is a rectangular hyperbola if this and this are same. That is, AA dash is equal to B, B dash. That is, A is equal to B is the condition, or length of transverse axis is equal to length of conjugate axis. Is how we define the rectangular hyperbola for a conjugate hyperbola. Therefore, in case of conjugate hyperbola being a rectangular hyperbola, both the hyperbolas pass through like this. Is how this is the original hyperbola, this is the conjugate hyperbola, which is also a rectangular hyperbola, provided this and this are equal. And we know that the rectangular hyperbola of this is equation of this hyperbola is x squared by a squared minus y squared by b squared equal to -1. Therefore, a equal to b implies I get x squared minus y squared equal to minus a squared. That implies y squared minus x squared equal to a squared is the equation of rectangular hyperbola, which is conjugate of the original hyperbola. So equation of rectangular hyperbola of a conjugate hyperbola is y squared minus x squared equal to a squared, as can be seen here. Now here, let's find the conjugate hyperbola in transformed form with all its properties. That is, if I have a conjugate hyperbola in the transformed form, then let's find the properties like foci, directrix, etc. for this transformed hyperbola in conjugate form. Now, as we know that this is in conjugate form because it's -1 on the right, I have Now this hyperbola is the conjugate form, and we know that it has the vertices b and b dash, but this is not x-axis and y-axis, but this is a transformed axis other than x and y-axis. Now here my center is hk, and my coordinates of b, which is 0b, will be h b k plus b and h k minus b, and I have a dash and a, which is a0 is how we get it. Now in this case, the focus, which is S, and the other focus, which is S dash, is given by 0 BE, that is H and K plus BE, and here it is H and K minus BE, is how each of it is transformed. Say for example, I want to find the directrix then this is given by y equals k plus b by e, and this is given by y equals k minus b by e in the transformed form. So each of the properties are derived through the formulae where length of major axis, the length of transverse axis of the conjugate hyperbola is given by 2b, and length of conjugate axis is given by 2a, and the rest of e square or e is root of a square plus b square by b square, are the one which we identify for the transformed hyperbola x square minus x minus h whole square minus y minus k whole square by b square equals -1 in its transformed form. Position of a point with respect to the hyperbola. Now, as in the previous case, we have discussed about the position of a point leading to three cases. One is the point lying inside the ellipse or parabola, and the point P lying on the ellipse and P lying outside the ellipse. Similarly, we define for hyperbola and its respective position of a point divided into three cases. 1, case 2 and case 3. where my hyperbola taken in case 1 case 2 and case 3. So in each of the 3 cases, as we have taken as case 1, case 2 and case 3, my case 1 has the point P, which is outside the hyperbola, and case 2 where P is inside the hyperbola, and case 2 is P is inside, and case 3 P is on the hyperbola. This. So with each of the cases, we identify that here P is outside, P is inside, and P is on the hyperbola. Mathematically, we have a formula where if I take the equation of hyperbola in standard form as x squared by a squared minus y squared by b squared minus 1 equal to 0, then we have 3 cases coming out of this point connected with standard equation of hyperbola. So in case 1, we say that P is outside if S11 is greater than 0. This is case 1 of the point. Now P is inside, then we say S11 is less than 0 out here. Now in case 3, P is on the hyperbola, so I have S11 equals 0 is what we get for the case 3. So each of the cases, case 1, when P is outside the hyperbola, S11 is greater than 0. Case 2, if P is inside the hyperbola, S11 is less than 0. Case 3, if P is on the hyperbola, S11 is equal to 0. Is how we understand the position of a point with respect to the hyperbola, divided into 3 cases, case 1, case 2 and case 3. Lateral recta or the lattice rectum, which is the plural form, read as lateral recta. Let's see what is the lattice rectum. Now in case of ellipse or parabola, we have defined the lattice rectum as a line or the chord which passes through focus and which is perpendicular to the major axis. Similar is the case where this is the line or the chord which passes through focus and perpendicular to the transverse axis. Let's see how the lattice rectum looks for the standard form of hyperbola. So when I draw the hyperbola, I have the hyperbola with center as origin, and of course its x-intercepts are AA dash, and this is B, and B dash with B is A root E square minus 1 is the distance what we get out here. The distance CB, which is origin, is A times root of E square minus A, where A is CA given out here. So this is A and this is B, and I have the equation of hyperbola is x square minus A square by minus y square minus B square equal to 1 with A greater than B. Now for here, we know that the foci are S and S dash clearly out here. So a lattice rectum is a chord which passes through focus and perpendicular to the transverse axis, that is x-axis out here. So if I drop a perpendicular and a chord to the hyperbola, then this is called the lattice rectum passing through S. Similarly, if I drop a perpendicular from S dash, I get M dash, which are called the lattice rectum. So L dash and M dash are called lateral recta for the given hyperbola. So with these two lateral recta, let's see what are the endpoints of the lateral recta. Now, as we know that the coordinates of S are AE, 0, then this would be AE, B squared by A. Coordinates of L is AE, B squared by A, and the coordinates of L dash are AE, minus B squared by A. Is how we get the extremities of the lattice rectum, as L is this and L dash is this. Similarly, let's find the extremities M and M dash for the other lattice rectum passing through S dash. Now clearly this would be minus AE, B squared by A, or minus AE, minus B squared by A. So there are totally 4 extremities, L, L dash, M dash, which are the extremities of the lattice rectums LL dash and MM dash respectively. And clearly I find that this length is the y coordinate, that is B squared by A, and this length is also the y coordinate, which is B squared by A, and therefore length of lattice rectum, where this is equal to this, has is how we get. So length of lattice rectum is B squared by A plus B squared by A, which is 2B squared by A. That is, length of lattice rectum is 2B squared by A units, and both the lattice rectums are equal, that is LL dash is equal to M dash. So lateral recta and their extremities and their length is what we have discussed in the session for the hyperbola in standard form with A greater than B. Equation of tangent. Let's see the equation of tangent for an hyperbola. That is, if I have an hyperbola in standard form, then for this hyperbola whose equation is given in standard form as x squared by a squared minus y squared by b squared minus 1 equal to 0 for a greater than b, let me take tangent t at p x1 y1, that is, this line touches the hyperbola at p x1 y1, and therefore we get the point of contact as p. Now I want to find the equation of tangent t at p x1 y1, which is given as equation of tangent t at p x1 y1 with respect to the hyperbola s equal to 0 is given by s1 equals 0. So the equation of tangent is given by S1 equal to 0, which when simplified gives x1 by a square minus y1 by b square equals 1 is the equation of tangent at p x1 y1 with respect to the standard hyperbola s equal to 0, and p is called the point of contact. This p is called point of contact, is how we understand the tangent at the point of contact p x1 y1. Now let's see equation of tangent in parametric form. Now we know that the parametric equations of the ellipse are x equal to a secant theta and y equal to b tan theta. Now let's see the equation of tangent in parametric form. Now for this ellipse, hyperbola, which has parametric equations as x equals a secant theta and y equals b tan theta for 0 less than or equal to this less than 2 pi, let me find the equation of tangent in parametric form. Suppose so here, this is the point of contact where the tangent exists. Now since I want equation of tangent in parametric form, I take the parametric point p of theta, that is a secant theta, and b tan theta. Theta is the angle made by the tangent with x-axis out here. So therefore, in order to find equation of tangent at p of theta, we are going to find using the formula. Equation of tangent t at p of theta with respect to the hyperbola and parametric equations is given by the equation x by a secant theta minus y by b tan theta equal to 1 is the formula for equation of tangent with respect to s equal to 0 is x by a secant theta minus y by b tan theta equals 1. Equation of normal. As we have seen the equation of tangent for the hyperbola, let's see the equation of normal at p x1 y1. For the hyperbola s, which is given by x square by a square minus y square by b square minus 1 equal to 0 with a greater than b. Now in this case, I have the normal which is perpendicular to the tangent and passing through the point of contact. So this is the normal which is perpendicular to the tangent. So n is the normal. So equation of normal at p x1 y1 with respect to the hyperbola s equal to 0 is given by the formula a square x by x1 minus b square y by y1 equals a square plus b square. So equation of normal is given by a square x by x1 minus b square y by y1 equals a square plus b square out here, where the normal is perpendicular to the tangent, is how we get out here the normal with its equation for the standard equation of hyperbola out there. Now let us take the special case of the vertices a and a dash. So what is the equation of normal at the vertices? So for example, I draw a tangent out here, then x-axis is perpendicular to the tangent. So if this is the tangent, this will be the normal, because this is perpendicular to this and passing through A. Now for the point of contact here, similarly, if I draw the tangent, then this will be the normal out for this tangent. Therefore, the exceptional case is that at a0 and a dash minus a0, equation of normal is x-axis, or the equation of x-axis being y equals 0. So equation of normal is x-axis or y equals 0, is how we understand the normal connected with the vertices as the special case. Similarly, let's see the equation of normal in parametric form. That is, if I take the hyperbola in standard form, and let me take the tangent at the point of contact P of A secant theta and B tan theta, which are the parametric coordinates. Then at this point of contact, we know that there is a normal which is perpendicular which is called the normal. Now, in order to find equation of this normal in parametric form, where theta is this in the anti-clockwise direction, then equation of normal in parametric form is given by equation of normal n at the parametric point P of theta with respect to the hyperbola s equal to 0 is given by ax by secant theta plus by by tan theta equals a square plus b square, and of course with the limitation that theta is not equal to 0 and pi, because if theta is equal to 0, we get x-axis, that is theta equal to 0 implies normal is x-axis, and theta equal to pi implies also normal is x-axis. So excluding these two exceptional cases of x-axis being the normal at A and A dash, we get the equation of normal given by this for all theta lying between 0 and t pi except at 0 and pi where the normal is x-axis. Condition for tangency. What is the condition for a line to be a tangent to the hyperbola? Or what is the condition for a line to touch the hyperbola is what we're going to discuss in this session. So the condition for tangency is related with the standard form of hyperbola, which I take out here with x and y, and then this, and then suppose I have a line which is a tangent to the hyperbola given in standard form, or as x square by a square minus y square by b square minus 1 equal to 0 with a greater than b, then the condition for this line to be a tangent is, for this line y equal to mx plus c to be a tangent to the hyperbola, this is c square is a square m square minus b square. So we have the condition for tangency for the line y is equal to mx plus c to touch the hyperbola. This is c square equals a square m square minus b square. Now let's find equation of tangent using condition for tangency. Now as we know that the condition for tangency is c square equals a square m square minus b square is the condition for the line y is equal to mx plus c to be tangent. We have c with plus or minus root of a square m square minus b square. That is, there are two values for which I correspond. So one is with c equals root of a square m square minus b square, and other with minus root a square m square minus b square. So how do we get these two lines is the biggest question. Therefore, c has two values, one given by plus and one given by minus, and therefore c equals plus or minus root of a square m square minus b square gives rise to two cases of the lines. So one of the line is y equals mx plus root a square m square minus b square, and the other is given by y equals mx minus root a square m square minus b square, one with plus and one with minus. So every pair of tangents are given with equal slopes. Therefore, the condition for tangency leads to equations of two tangents, one given by y equals mx plus root a square m square minus b square, and there's another tangent which is parallel, and then that is given by parallel to this, and that is given by the equation y equals mx minus root a square m square minus b square are the two pairs of tangents, parallel tangents, which we have given by two equations. T1 parallel to T2, and equations of tangents are given by y equal to mx plus or minus root of a square m square minus b square is how we identify the tangent of the hyperbola. Also, as we see that there's something inside the root, therefore continued out here, I get for a square m square minus b square greater than 0, or m square greater than b square by a square, there exists always two tangents which are parallel to each other. There always exists two tangents which are parallel to each other in pair. In pairs is how we understand the property where this tangent is parallel to this given by plus or minus, and is how we understand the pairs of tangents. There exists at least one pair parallel to each other and given by the condition for tangency.